All right, let's do a couple more definite integral examples. So here I've got a polynomial. Those are pretty easy to take the antiderivative of. We're just going to use power rule over and over again. We're going from -1 to 1, and these will be x values. I know that because the dx tells me my variable of integration is x. So there's an x, there's an x. And this is implied that I really have parentheses around this whole thing. Now I could, if I wanted to be very pedantic, I could split this integral up into 3 separate integrals. And sometimes that's beneficial to do. There will be plenty of times when we'll write this out. -1 to 1. That we'll do this all the time, where we'll write out 3 separate integrals because maybe one's easier to do than the other ones. Maybe we have to do something really complicated like integration by parts on one part, and we just want to deal with that separately. But in this case, it's not necessary to write this. We could just do each one and evaluate all at the end. So the antiderivative of 2x cubed, that 2 comes along for the ride, x cubed, that power raises by 1, and then you divide by the new exponent. Antiderivative of 5x will be 5x squared over 2. His exponent was 1, goes up by 1 to 2, divide by the new exponent. And then this is the one that's going to get you. The antiderivative of 7 is not 0 or just 7. It would be 7x evaluated from -1 to 1. Now we plug in 1. But again, there's more than one way to write this out. I could plug in top minus, plug in bottom, all into the first. Top minus bottom in the second. Top minus, I could do it that way. You're more likely to make a mistake that way. My recommendation, plug in the top number into all of them. Let's simplify this fraction. That's 1/2. 1 to the 4th plus 5/2, 1 squared minus 7 times 1. Minus, it's always top minus bottom. Plug -1 in for all your x's. 1/2 -1 to the 4th plus 5/2, -1 squared minus 7 times -1. And then clean things up slowly. It's this negative right here that's going to end up messing you up. So you got to make sure these parentheses here are very clear. So sometimes I like to clean everything up in here, just get a number, 7/4 or whatever it is. Then I don't have to distribute this negative. Other times when I see that things are going to cancel out, I'll distribute like this and this are going to cancel. So is this and this because of that negative. So here, let's clean some stuff up. 1 to the 4th is just 1. 1 squared is just 1. 7 times 1. We got that minus there, so -7. And then this guy here, so I'll write these out. This will be 1/2 plus 5/2 plus 7. And then I've got my parentheses here. So -1 squared is +1, -1 to the 4th is +1. Now all of that's going to get subtracted. So I'm going to distribute that minus because I see ahead of time that guy's going to cancel that guy. He's going to cancel him, and so forth. Well, that actually not so forth, just those two. So what do we get? 1/2 plus 5/2 minus 7 minus 1/2 minus 5/2 minus 7. Those canceled. Those canceled. These don't. That's -7 plus another -7, -14. So what that means is if you were to graph this function out, like I don't know that I'm not saying this graph is right, but I know he's got a bunch of negatives. So I don't know, maybe he's like that. So maybe here's -1 and +1. This area right here will be a net negative. Maybe there's some that was positive and some negative, but the area between this curve and the x-axis from -1 to 1 has a net area of -14, meaning there's 14 units of area below the axis more than whatever there was above. Okay, let's do another one. The only rule, no, like we've done sine and cosine. I think in another video we did something with the antiderivative of e to the x is e to the x. We're going to do natural logs in a future video. Other than that, the only rule we know is power rule. So I want to write this guy as u raised to some power. Notice I'm integrating with respect to u. U is my independent variable here. So I want to write this as u to some power. So I hope you agree that that's u to the -1/4 power. du. I have to keep writing du. Every time I write an integral symbol, I have to have a differential here. These two go together. This is really one symbol. This thing here is attached to, it's glued to that. You'll never have that without that attached to it. Okay, let's do this guy. This definite integral, I'm going to have u. My power is going to go up by 1. So I'm doing -1/4 plus 1, which is 4/4. That will be +3/4. Dividing by the new exponent. The exponent raises by 1, and you divide by the new exponent. Evaluated from, this is a definite integral, so I don't write plus c. Evaluated from u equals 1 to u equals 16. Okay, and we'll do the evaluation in a minute, but let's do a quick check. How could I check and make sure I did that right? Well, I could take the derivative with respect to u, use my independent variable of this stuff here. Derivative, now we got to think back. See, you're going to get confused with this when you first start doing antiderivatives, because you've been doing derivatives all semester long. You've learned all these rules. Now you're trying to think of them backwards. And now right at this moment, I'm trying to go forwards again. This is derivative. You bring the power down and then drop the power down by 1. 3/4 minus 1 would be -1/4. And this fraction cancels. I get exactly what I was supposed to get. Definitely go through this. Convince yourself that the derivative of this is this. All right, now I would clean this fraction up. What's it mean to divide by a fraction? Multiply by the reciprocal. All right, now we plug in the top. So this 4/3 is just coming along for the right. I'm going to write it at each step, but I could factor this 4/3 out and just do, in fact, I'm going to factor the 4/3 out. Plug in a 16 minus plug in a 1. So I just pulled the 4/3 out, plugged in the top, minus plugged in the bottom. 16 to the 3/4. That means take the 4th root of 16, which is 2, and cube it. That will be 8. 1 to the 3/4 1 to any power, it's just 1. So this will be 4/3 times 8 minus 1. That's 7. So 28/3 is our final answer. So this guy's graph, whatever he looks like, if I were to find the area under the graph, he's always positive. So there wouldn't be any negatives. He is a 1 over a cube root. So he's actually an increasing function. If I go from 1 to 16, he's, I don't know, maybe something like that. I don't know. Whatever his graph looks like. That's not what's important right now. The area under that graph from 1 to 16 is 28/3. That is cool. You got to admit that that's pretty cool, that we can have some function. Like, I would have to really think about how to even graph that guy, much less finding the area underneath it. And it's just this simple work here. This really was not very complicated mathematics once we know the fundamental theorem of calculus part 2. This is really powerful stuff. All right, that's a good place to stop.